Hey guys, so this is going to be the first lesson on trigonometric identities. You'll have to correct me if I'm wrong, but I believe you will have looked a little bit at some trig identities in grade 11. I'm just going off my own memory from when I was in grade 11. I haven't taught the grade 11 course before, so you'll have to let me know if I'm going too fast or anything. But we are going to start basically from the beginning. We're going to start looking at some equivalent trig expressions. So this shouldn't be too far of a leap from what you've learned the last 2 years with the different quadrants around the unit circle. So we're going to start off looking at the sine function, and actually we're looking at f of x equals negative sine x. We have a vertical reflection, so a reflection across the x-axis. Normally the sine function starts at 0 and goes up. This one goes down and still has a period of 2 pi. So we have f of x equals negative sine of x. Or we know we normally start at the x-axis, at the axis of symmetry, and go up. We could also think of this as f of x equals sine of x minus pi. We could have everything shifted to the right by pi, or even to the left by pi if we did x plus pi. Those are all function names that could be used for this function. We could also look at this as a cos function. Cos functions, we always start at the top at y equals 1 or f of x equals 1. So this could be a cos function that's shifted to the left negative, or to the left by pi over 2. So this could be f of x equals cos of x plus pi over 2. Or we could shift it right, our regular cos function to the right, and then reflect it down. So this could also be f of x equals negative cos, a vertical reflection, and x minus pi over 2. We're shifting to the right pi over 2. So these 4 different functions, they all describe this graph. So because sine and cosine functions are periodic, there's many ways to describe the same graph. We can write it in an unlimited amount of different functions. And so we're also going to look at equivalent expressions using the fact that the period is consistent. So for this cosine function, we know it's cosine. We're starting at our maximum and then going down to our minimum. So this is just our base f of x equals cos of x. If we shift everything to the right by 2 pi, now this point would come here, this point would come here, we get the exact same function as well. So these functions both describe this graph here, this poorly drawn graph. Or if we shifted to the left, we'd also get the exact same graph. If we're shifting sine functions or cosine functions by the period, left or right, we get the exact same function. We can shift it by more than one of the same period. We could shift it to the right by 4 pi. If we shift everything to the right, this point will come all the way to here. This point will come all the way to here. This point will come all the way to here. Same with the bottom. Our low point will come all the way to here, our minimum. So these are all describing the same thing. So these are all equivalent expressions. These would all equal each other. And on the filled out lesson, there's also sine, same thing. If we subtract or add 2 pi, we get the same. For tan, because tan's period is pi, tan of x would be the same as tan of x plus or minus pi. And so on. So this, we can kind of look at the what we know about quadrants as well and come up with some more equivalent functions. We'll look at some equivalent expressions with principal and related angles. For the first quadrant, we're going to compare everything to the second quadrant. So in our second quadrant, here we are always looking at our angles were pi minus our related angle. And so for sine, because sine is positive in this quadrant, sine of pi minus theta is the same as sine of theta. That is always true. Cos of pi minus theta. Well, cos was negative in this quadrant, so that's going to be negative cosine of theta. And same with tan. Tan of pi minus theta is going to be negative tan of theta. So here we get another 3 equivalent expressions. We can do the same in our third quadrant. If we look at an angle all the way into the third quadrant, we're looking at theta to the x-axis. So we're looking at all of our angles as being pi plus theta. And we're going to relate all those to our first quadrant. So in this quadrant, we have tan is positive, so that means sine and cosine are negative. So we get another 3 equivalent expressions, and we can do the same thing for our fourth quadrant. We're looking at 2 pi minus our theta. And in this quadrant, cosine is positive, sine and tan are negative. So we get 9 different equivalent expressions that we can use to simplify certain angles. Sometimes that'll help us, and we'll look at different identities that might involve that as well. So turn the page here, creating equivalent expressions with odd and even functions. You would have talked about odd and even functions at least, I would hope, at the beginning of the year when you were first talking about polynomial functions, and I'm assuming you've talked about them in years past. So odd and even functions, we're talking about the symmetry of the functions. So even functions, always have symmetry across the y-axis. So when you're talking about polynomial functions, that would have been any polynomial function that had an even power is an even function. I guess not any even polynomial, but like your base even degree polynomials. So like y equals x to the 4, y equals x to the 6, and so on. Once you start adding other terms, it gets a little messier. But for instance, if we had a function that looked like this, an absolute value function, that would be even. Any point on the positive side of x, let's say that, what do they give an example for? If we have an x equals 4 and our y equals 4, then on the other side, for x equals -4, we're going to get that same value. Even functions, everything's reflected over the y-axis. So if we take f of -x, that's always the same as our f of x. Even functions, they're symmetrical across the y-axis. Odd functions, your odd degree base functions, y equals x cubed, y equals x to the 5, those are odd functions. An odd function, so we'll look at a cubic. Odd functions, if we have a point at, the example they give is -2, 8, so looking at just our y equals x cubed. On the other side, at -2, we're going to have a point at -8. So when we take our f of -x, we get negative f of x. And this creates rotational symmetry. So odd functions, if we rotate them around the origin, we get the same function back. Even functions, when we reflect over the y-axis, we get the same function back. So our sine function, which, this is going to be a very rough drawing. We start at our origin, we go up and start our periods. So this definitely isn't an even function because we can't reflect it and get the same function back. But if we rotate it around the origin, we get the same function back. The example they give in your lesson, sine of -3 pi over 2. So if we go pi over 2, pi, 3 pi over 2, that gives us +1. Sine of 3 pi over 2 is going to give us pi over 2, pi, 3 pi over 2, we get -1. So our f of -x, where our x is 3 pi over 2, that's +1 is negative of f of x. That was our odd symmetry. So sine functions have odd symmetry. Sine of -theta equals negative sine theta, always. And no matter what theta is, this is always true. Cosine we'll do another rough sketch. We start at our maximum value and then complete our periods. Not the best drawing, but if we look, any point across the y-axis should have a match on the other side. For instance, if we look at cos of -pi, so -pi over 2, -pi, that equals -1. If we look at equals -1. If we look at cos of pi, pi over 2 pi, that's also equal to -1. So our f of -x equals our f of x. That was what happened when we had even functions. So this is, cosine functions have even symmetry. Cos of negative theta, sorry, always equals cos of theta. If we're taking cos of a negative angle, we can always rewrite it as cos of the positive of that angle. They're always equal to each other. They are equivalent. And finally, we'll look at tan. Yes, right now. Tangent. Our tan function. We had this repeating over and over with asymptotes. Again, this is a very rough sketch. Look at tan of negative pi over 4. So again, these asymptotes, this is at pi over 2 and negative pi over 2. So tan of negative pi over 4, can't really tell this from the drawing, but tan of negative pi over 4 would equal -1. Might have to go back and look at our notes if we don't remember that off the top of our head. Tan of pi over 4, again, we're halfway to our asymptote. We're at +1. So we can see our f of -x is negative of our f of x. That's telling us that we have odd symmetry. Again, we have that rotational symmetry. If I rotate my tan function 180 degrees, I get the exact same function back. So tan of negative theta always equals negative tan of theta. We can see these three things also if we look at our fourth quadrant. We're looking at negative theta. This is the quadrant where cosine is positive. So it makes sense that sine of negative theta and tan of negative theta equal negative sine of theta and negative tan of theta. They're both negative in that quadrant. Cosine of negative theta is positive in that quadrant. So that's why for it we get even symmetry and we get odd and odd for sine and tan. Those are our three more equivalent functions. The last piece we're going to look at today, or for this lesson, I guess, is our cofunction identity. Should probably look at what I'm spelling. Cofunction identity. So we're creating equivalent expressions with complementary angles. Complementary angles are angles that add up to 90 degrees. So if we have an angle theta, we have to add up, if we're talking about radians, we have to add up to 180 degrees. We have to add up to pi. Our 90 degrees is pi over 2. These two have to add up to 90. So pi over 2. So this is going to be pi over 2 minus theta. Pi over 2 minus theta plus pi over 2 plus theta will give us pi. For our sine of theta is opposite over hypotenuse. So we'll label these based on theta. If we look at cos, I guess I shouldn't label that. If we compare that, that will be equal to the cosine of pi over 2 minus theta, which was for cosine, it's our adjacent over our hypotenuse. This adjacent for this angle and this opposite for this angle, it's the same side. So these are the same ratio. So sine of theta has to equal cos of pi over 2 minus theta. Doesn't matter what this angle is. These ratios are talking about the same two sides. Similarly, we can look at our cos of theta, which would be our adjacent over our hypotenuse. And if we compare that with sine of pi over 2 minus theta, that opposite is the same side as our first adjacent, and our hypotenuse stays the same. So cos of pi has to be the same as sine of pi over 2 minus theta. Those are equal to each other. Finally, tan of theta is our opposite over our adjacent. The other function that's going to use those two sides, using pi over 2 minus theta, is going to be cotangent. Cotangent of pi over 2 minus theta, cotangent's opposite of tan, so it's adjacent over opposite. The adjacent of this angle is the same as the opposite of this angle. The opposite of this angle is the same as the adjacent for this angle. So these are the same as well. So tan of theta has to be the same as cotangent of pi over 2 minus theta. So right now we're just establishing some equivalent expressions. We're going to get into how we're actually going to use these expressions in the future. But for now, just want to introduce the fact that because trig is so repetitive in that we have periodic functions, periods are all the same, they follow the same pattern, we're simply just shifting things around. We get all of these different ratios popping out that will become useful. I'll leave this here for now, and you'll hear from me in lesson 2. But for now, have a good day and goodbye.